in her university, and I will say that I have been visiting the Institute of Patricia, and I must say this is absolutely true. The team is enormous, and the young people, the brand young people there working with Patricia is a big team. So thank you, Patricia, for visiting us.
Thank you very much for having me here. It is a pleasure to be here again. I mean, I have been. I think I was here in 2009. 2009. Yes, I'm going to give you a brief summary of our results, of some of the results that we have on chemical evolution. But first of all, I want to introduce my team. I am really very proud to have an excellent team of young researchers, PhD students, and postdocs. And I always think that I should prepare a talk with a slide from everyone, but at the end I don't do that. But at least you got their faces. I'm going to present some of the work of Brian Tapia, who is here and who is now working on one of the subjects that I have been working for a long time. But to introduce the topic, what we do is we use numerical simulation, hydrodynamical simulations to follow the evolution of galaxies. And as you know, this is a very complex process. We need to introduce the large scale structure information plus what is going on at even stellar scales, and the time, the different physical processes with different lifetimes or different time scales are complex to resolve numerically. So we use a set of what we call subgrid physics to model the formation of stars, the cooling, the formation of gas, the transformation of gas into stars. And of course, at some point, we started to introduce the evolution of stars from the chemical point of view. And I think this is a very important piece of information. If we can actually reproduce a galaxy that looks like a galaxy, that have the velocity distribution, the stellar population, and also the chemical information in the stellar population and in the gas, because it provides much more detailed information for two things: to compare observations and simulations, and to validate the models, and also it's a powerful tool to understand the action of different physical processes. But it is very complex to do it from a numerical point of view. So we have to take into account all these different processes, as I mentioned, the growth of the structure, the inflow, the mergers, the interactions, and then the gas cooling and condensation within the potential well of the system, the star formation. Then we have a recipe to introduce the stellar evolution. And from there, we also need to include AGN and supernova feed to account all the environmental effects where the galaxy forms. I mean, if it forms in a filament or in a cluster, the evolution will be different. So the advantage of using numerical simulation is that we have all of this. I mean, the part of this, this part, more or less given and very well understood. And then as we move to the star formation, stellar evolution, and feedback, then things get a little more messy, and there are a lot of recipes and free parameters to fix. But I think at the moment we have reached a point where numerical simulations are able to reproduce some of the observations, and then they are actually a powerful tool to make predictions and try to understand how galaxies form and evolve. Sorry. So why chemical elements? Well, I think what most of you already, I don't have to convince you that because chemical elements are produced by different or have different progenitors, and these progenitors have different lifetimes of evolution, having the information of the combination of different abundances, or chemical abundances, provide us with time scales that we can actually compare with observations and try to understand or try to extract information on the star formation history, for example, or the impact of gas inflows and the mixing of different chemical elements. So this is why we started introducing first the supernova 2, then the supernova 1A, then the NGBs, and probably the R processes, R capture processes in the near future, to try to be able to reproduce these observational abundances in a sense. I'm going to get into detail later, but the idea will be to have abundances that we can actually compare with observations, so because we have the whole picture of galaxy formation, try to understand the impact of the different physical processes. So one of the properties that we have studied for a long time are metallicity gradients, okay? And we know from, if we take a normal galaxy, a normal spiral galaxy, we expect to have a negative metallicity gradient if we look at the H2 regions. So this is, we can reproduce this in observation, in the simulation, sorry. And we have if we have a nice galaxy, a spiral galaxy, you can actually see here in the simulation the spiral arms. And we have, this is the density distribution, the environment of the galaxy, and here the oxygen over hydrogen projection maps, phase on and H on. And we measure the gas, the star-forming gas in the simulation, and we can reproduce this negative metallicity gradient, which is consistent with an inside-out formation. And this has been done by several models and different ways of simulating the star formation, the cooling, and even how the chemical evolution is introduced. In the models are slightly different, but in general, we can reproduce this property of galaxies, okay? And they are comparable. For example, these metallicity gradients are comparable with observations. This is a compilation by Mercedes Moja for the Milky Way, and you can see that reproducing a negative metallicity gradient is something that can be well understood in the simulations, and they reproduce observations. Now, if we go to a more statistical basis, and we take for example, the results from Belfiore et al. From Manga, where he estimated the metallicity gradient in galaxies of different masses and a large sample. So now we can see here that there is a variation of the metallicity gradients. So here we have the metallicity gradients normalized by the effective radius as a function of the stellar mass. And you can see that there is, at a given mass, there is a large diversity of metallicity gradients. And also there is, on average, the median values tend to determine this kind of a U-shaped value, where as we move from masses with galaxy with masses larger than 10 to the 10, the trend will be to get flatter metallicity gradient, while if we go to low mass galaxies, they also tend to be like flatter. But in general, I would say that the trend is quite noisy, and at a given mass, there is a diversity of metallicity gradient, which means that there are different history of formation of galaxy, different history of evolution, and maybe these metallicity gradients are actually reflecting this different evolution. And also, I'd like to point out that there is a fraction of galaxies, okay, like about 10 to 15% of the sample that shows this inverted metallicity gradient. So these galaxies, instead of having this negative metallicity gradient that I showed at the beginning, which are consistent with an inside-out formation, they have the inverted one. They are less enriched in the center and more enriched in the outer parts. And this is something that caught my attention because I found it interesting that something has happened to this galaxy that actually their H2 regions are inverted. Okay, so keep that in mind. Now this is a compilation of metallicity gradient at redshift 0. If we do the same at high redshift, and this is a compilation of all the metallicity gradients at that time, 2022, that were available or measured at different redshift. Again, the gradients as a function of the stellar mass, and you can see that the trend, there is no trend, no? There is like a messy distribution, where there is no clear dependence with the stellar mass. The points are the observations, the symbols are the observations, and then the shaded regions are results from different numerical simulations. And you can see that from the numerical point or the theoretical point of view, there is also there is no trend. There may be a slight trend from fire simulation, which is this one here, to have an increase of or a flattening of the metallicity gradient for smaller masses. But in general, they agree in the sense that there is no clear trend. You can see here two lines, okay, here and here. And these lines are results from the EAGLE simulations. And these results, these different trends comes from changing the strength, the strength of the supernova feedback, okay? So what they did is they ran the same initial condition with a weak supernova feedback and with a strong supernova feedback. And then what we did is we measured the metallicity gradient with these two different kind of supernova feedback. And we got opposite relation. You can see that here there is a positive correlation with the stellar mass, and the other one shows a negative correlation with the stellar mass. And the thing is that the negative one was obtained with a strong supernova feedback. If we use or we modulate the galaxy formation using a very strong supernova feedback, then this feedback is able to eject a lot of material from the center of the galaxy and invert the metallicity gradient, change the direction of the metallicity gradient. So we have this information that was also found in previous work, where the strength of the supernova feedback modulates the distribution of chemical elements in the galaxy. So the question is, what information are actually stored in these metallicity gradients, and how can we retrieve this information from this observation, or even the simulations? How can we link these two things? So these are the two main questions that we have been asking for a long time. What processes shape the metallicity gradient, and what information is stored by this metallicity gradient? It's actually what is really left. And we know that first, when we have an inside-out formation, a scenario for the formation of a galaxy, we will have these negative metallicity gradients. But we also know that galaxy interaction, mergers, supernova feedback, maybe AGN feedback, gas inflows, which means, with gas inflows, bars, cold inflows, maybe even galactic fountains in any directions, even stellar migration can actually mix up the chemical elements in the galaxy and even the stellar populations. And this will modulate or maybe change the shape of the metallicity gradients. The thing is that they don't act individually, separately, but they act maybe all together or combined, and it's very difficult to disentangle the action of each of them and the efficiency as a function of redshift. So as the galaxy evolves, we expect them to be always present, but their impact may be different at different time of evolution. So in the case of a merger, we study them in detail by using not cosmological simulation, but what we call prepared simulation. So we can, with this prepared simulation, we can take them and put them in interaction and study in detail how how everything changed, the distribution of gas, the distribution of gas in condition of forming stars, the star formation activity, and the metallicity distribution. So we started with a galaxy that has a very well-defined disk with a very well-defined metallicity gradient. And we can see that as the evolution, as the galaxies interact, there are many things happening. Actually, the galaxies get distorted, the arms get open, depending on how the orbital parameters, because depending on the orbital parameter of the encounter, the impact of the merger will be different. And you can actually see some, I don't know if you can see it actually, but there are different circles with different colors, okay? And these are the sites of star formation. So there is a star formation going on the arms that are being distorted, and also in the central region and in the bridge And when we measure the metallicity gradients of the galaxy, we can see that the shape of the galaxy change. The shape change the level of metallicity and the shape in the central region and in the outer part. This is because of the material that is being redistributed either by the dynamical effects, the tidal effects of the interaction, and also the supernova feedback. So when we put them together, like here, you have the evolution of the metallicity gradient from the first pericenter to the second pericenter. And you can see that it decreased because at the beginning we have the inflow of gas coming from the outer part, which are lower metallicity. But then it changes again, it gets enriched again about the first pericenter, because this gas that flows in triggers a star formation. And with the star formation, we have a lot of massive stars form, and the injection of oxygen is very quick. So you have again a steeper metallicity gradient in the inner part. And then with this new supernova feedback, you have ejection of material. And when the material is ejected, then the metallicity decreases again. Okay. So the metallicity, the level of enrichment and the gradients in the inner part change, and they also change in the outer part, because we can follow these particles and they go, some of them are ejected and they go away, but some others are pulled down and are created in the outer part. So the outer part of the galaxy gets flatter because of two reasons mainly: the galactic fountain and the disruptive material that are exchanged from the companions. I have put a lot of processes here because they are the processes in these three squares. It's are the processes that we are taking into account in the simulation. And in this other yellow box, we have the processes that are missing. For example, in this simulation, we don't have gas inflows from the circumgalactic medium, we don't have AGN feedback, and we don't have cold flows. So even in a very simple scenario where we have two galaxies and we control almost everything in the simulation, the metallicity gradients change very in a very complex way, in a very simple physical situation where you have two galaxies and they equal galaxies, exactly the same one, and they interact. The metallicity gradients are very, very complex. Now we want to understand this in a cosmological simulation. So where we have different mergers, different orbital parameters, gas inflows through filaments, and a large scale environment. So understanding what the metallicity gradient gives us is very complex. Okay. So this is a compilation now, again, observation of the metallicity gradient, but now as a function of time. Okay, so we have redshift and metallicity gradient, and this is a paper from Venturi 2024. So it's more or less, these are the metallicity gradients that we know up to redshift 8. Okay, so now we can actually try to, with a lot of maybe with caution, but we have an idea, or we start to have an idea. I don't want to be very, of the metallicity gradients. Metallicity gradients measure a very high redshift, okay? From redshift 0 to redshift 8. Okay? And you can see that here at redshift 0, most of the galaxies have negative metallicity gradients, or even flatter metallicity gradient, with some 10 or maybe 15% of inverted metallicity gradient. But as we move to higher redshift, it looks like this fraction of, or this category of inverted metallicity gradients increase. Okay? It seems that there are more galaxies that have this flattened or inverted metallicity gradient, positive ones. A larger fraction of these galaxies are present at higher redshift. And again, the symbols are the observations, and the boxes are also the observations, and the simulations are the lines. Okay, and you can see that there are almost no simulations at the redshift, because these are very high redshift, and it's very difficult to actually simulate galaxies at those very high redshift. So the resolution of the simulation allows us to more or less reproduce or study the metallicity gradients up to redshift 3, 4, maybe 7. But 7 there will be 2 or 3 galaxies that can be reached in a simulation to this very high redshift, the more massive ones. So what we get from here, from the observational point of view, the diversity of metallicity gradients of change with redshift, and it seems that there are more inverted metallicity gradients at high redshift. And from the simulation, we have different predictions, which depends mainly on the strength of the supernova feedback. So from these different simulations and our own study, we got these predictions or these ideas. I mean, I would say, first, we know that there are negative metallicity gradients when the galaxy can form inside out, which is what we expected, and we already talked about that. But if we have strong supernova feedback, maybe AGN feedback, I don't know, but at least supernova feedback I know, and strong gas inflows and supernova feedback, then we can invert these metallicity gradients and have this trend and reproduce this trend with observations. So this line, the red one, is a simulation from EAGLE simulation, and this EAGLE simulation has an efficient supernova feedback. It also have AGN feedback, so both AGN and supernova feedback in the simulations work together, and it's not so easy to disentangle which one is is actually producing this inversion of the metallicity gradient so far. So because it is a complex problem, we thought at some point to start our own project, our own simulations. We call it the CIELO project. And the CIELO project aims to study normal galaxies and between Milky Way and Milky Way galaxies in different environments, not in cluster, in filaments, in voids, and walls. Okay, and we took the galaxy, like a target galaxy, and the environment, so we can simulate at the same resolution not only how the galaxy formed, but also how the environment evolved. And we follow this with our own version of Fecha 3. We have a multi-phase model, a star formation model, metal-dependent pooling, initial malfunction. We change the chemical evolution. We include supernova 2 and 1A in the simulations that I'm going to talk about, but the new rounds also have AGVs. So at the moment, we have like 54 central galaxies with their satellite galaxies, and these central galaxies have a mass between 10 to the 8.5, some of them are quite small, to 10 to the 10, I would say 10 to the 11, but I was very conservative with the masking. So what we want to do? Well, as you can see, we have the galaxy. This is a normal galaxy, spiral, very well-defined disk. And you can see, again, the density distribution of the gas. This is the total gas and the stellar population. Here we have everything together. And here we have the metallicity of the gas. And you can see this is a galaxy with an inside-out distribution of metallicity gradient. And if you look at H on, you can see the outflow, enriched outflow of the material that are being ejected or were ejected at different time of evolution of the system. And the lines shows the velocity distribution of the gas surrounding the galaxy, so you can actually see how the gas is expelled or how it comes back to the galaxy. So we wanted to study the metallicity gradients and see how they change in time and from where the gas comes from, okay, and the metals come from. So first of all, we validate the simulation. I'm not going to get into detail, but the simulation follows, the galaxies follows the expected mass-size relation, mass-metallicity relation, enthalpy relation, and the star formation. And with this galaxy, then we follow them back in time. You can see here redshift 0, the same galaxy that I showed you before. The progenitor are redshift 2 and the progenitor are redshift 6. Note that the color change, the bar color change, no? Because it gets lower and lower metallicity. But you can see that at redshift 6, the galaxy that redshift 0 is a very well-defined spiral. At redshift 6 is a series of clamps along filaments, so with a very messy structure. So defining what is a galaxy at that time is kind of difficult. So at redshift 0, we have a galaxy in general that as I say, spiral galaxy, negative metallicity gradient that we can reproduce quite well. And now I'm going to talk about the work of Brian Tapia, who is here. But if we take, there is a part of the plot that I'm missing. It's not much, but it's not much. It's just a very small piece and heroes. But anyway, you can see that if we take different galaxies, they have different metallicity gradients. Okay, so we have galaxies that have breaks, and they cannot be reproduced by a single power law, like in this case. So this break can be in different regions. It can be in the outer part of the galaxy or in the inner part of the galaxy. And we have also galaxies that have these inverted or positive metallicity gradients, and they have this kind of ring at some time of their evolution. Okay? And other galaxies that have two breaks. Okay, so they need 3 power law to be able to reproduce correctly the distribution of chemical elements in the star-forming regions. So for our sample, this is a statistic. 33% are fit by a linear, by a single power law. 41% have an outer break. So this break is in the outer part of the galaxy with respect to the half mass radius. And other galaxies, like 50%, have inner breaks, and 10% have a double breaks, okay, like this. So we wanted to understand why this, what is going on. Okay, so let me define these 3 regions now, because when we have this galaxy with 3 power laws, it's very easy. We have the inner region that defined by the first gradient, the middle region, and the outer region. Okay, but as I mentioned before, not all the galaxies have 3 regions or 3 power laws well defined, but we are always going to talk about 3 regions, okay? Because we will use, if we don't have a break, like in this case, an inner break and an outer break, we will use the half mass radio to define this region, okay? So everything that is from the center to the half mass radio will be the inner region, and from the half mass radio to the one half mass radio and 2 will be the second region, and then everything which is further away will be the outer part. So if we have 3 breaks, they're well defined. If we have 2 breaks, depending if it is in the inner part or in the outer part, we define the missing region, okay, by using the half mass radius. And why I'm explaining this? Because I'm going to use this later on. So first of all, we measure these metallicity gradients. As I mentioned, using this, we fitted this distribution by using an automatic algorithm. This automatic algorithm search for the best description of this metallicity gradient. So it actually decides when you need 1 power law or 2 or 3. And with that, we compare with observation, okay? But in general, observers use 1 single power law between 0.5 half mass radio and 1.02 half mass radius, okay? So that part, that region is what we call the middle region, okay? So in order to compare our simulations with observation, we have to compare the gradient that we obtain in the middle region, okay? And this is what we plot here. This is the gradient in the middle region. The field circles come from the observations, and the open symbols come from observations. Did I say? Yeah. The field ones, simulations, the open ones, observations. Well, as I mentioned before, we have a sample that goes from about 10 to the 8 to 10 to the 11 solar masses, and observations tend to have higher masses. But in general, the gradients that we recover from the simulations compare well with observations, okay? And as I mentioned here, I'm showing the middle, the metallicity gradient in the middle region. But we can also, what we did is we also forgot about these breaks and fit 1 single power law, okay? And this is shown here in the lower plot. And you can see that if we use a single power law, we also get similar results. So a single power law, although doesn't take into account the inner breaks and the outer breaks, more or less reproduce what is going on in the middle region. And it is comparable with observations. We also try to compare the gradients that we obtain in when we have an inner break and an outer break with observations. There are not many observations that have measured this. So again, here you have open symbols or observations in both cases. And we can see that what we obtain from the simulations are following similar trends as a function of the stellar mass, a function of the specific star formation rate, as a function of the half mass ratio. And you can see that more or less they are within the observed relation. We have a larger dispersion here in a low mass, okay? So there is a larger variety of outer breaks. We have negative, galaxies that have a negative metallicity gradient in the outer part, but sometimes they are positive. Okay. So as I say, what we wanted to do is to actually follow the evolution of these galaxies, which are all the time interacting with the environment, experiencing or having mergers, minor mergers or major mergers. So what Brian did actually was to take all these galaxies, each of them, and follow them back in time, and follow the galaxies, the mergers, and the interaction. So some galaxies interact and they are surviving satellites, and some others interact for a while, and then at some point they merge. He did it for all of them. I'm only going to show you two of these results because I want to focus on the processes. Okay, so you saw that this is a very messy evolution. Okay, so at each time of interest, so we have the simulation, and for each simulation, each of the simulation that we run, we have different snapshots, so we can follow the evolution of these galaxies at different times. Okay, but these are like maybe 100 snapshots of the evolution. So at each of these time, what Brian did is to follow the progenitor. Okay, he searched for the progenitor. He took the progenitor galaxy. He actually defined the disk, if there is always some kind of disk, and defined the angular momentum of the disk, and rotate the galaxy so the plane of the disk agrees with the plane of the X. No, and so he can define the plane of the galaxy, and then he defined the three different regions. Okay. And he also followed all the particles that are part of this galaxy back in time to see if these particles, the gas particles, comes from the circumgalactic medium, come from the same galaxy, but flows, go from the outer part to the inner part of the galaxy, or from the inner part of the galaxy to the outer part. So inflows or outflows. And he also followed the particles to see if the gas comes from unbound gas that comes directly from filaments or are never shocked to the virial temperature of the halo. Okay? So if the gas is pulsed and is shocked and becomes part of the virial ice, so gets to the virial temperature, then we consider it as part of the circumgalactic gas. Okay? So we have 1, 2, 3, 5 different channels to feed the galaxy with gas. Okay, and these are different paths will bring gas with different characteristics and basically different metallicity. I forgot also that he follows the satellite, as I mentioned, so he can also know if the gas has been disrupted from a satellite galaxy. Okay, so we more or less have a very clear idea of from where the gas comes and how it moves. So now we also measure the metallicity gradients at each of these times. Okay, so we have this like 100 times where we can observe our galaxies. Here there are 2 galaxies. Okay, and we measure at each of these times the metallicity gradient and decide if the metallicity gradient is broken or not, and in how many pieces it is broken. So here you have in black, the lines shows the middle metallicity gradient, and the green or teal shows the inner gradient, and orange the outer gradient. Okay, so if we have three gradients, it is very easy to understand. Otherwise, we're considering a galaxy that is broken in two pieces, and the breaking radius could be the inner part or the outer part of the galaxy. So you can see that the galaxy does a very complex path, or determines a very complex path. Okay, at high redshift, there is a lot of variation of the metallicity gradients, all of them. And for about redshift 1, it starts to converge to more or less a flat metallicity gradient. And if it has like an interaction here, this is a region, the shaded region shows the regions of either merger or interactions. This merger of interaction can alter the metallicity gradient, but not all the time we can associate a change of the metallicity gradient to a presence of an interaction. Sometimes are gas inflows, or maybe the formation of a bar by secular evolution. But we can actually, as I said, because we determine from where the gas comes from, now we have this evolution of the metallicity gradient with the breaks, so we can actually look at, in the same time interval, we can look at the from where the gas came from. So we follow the same color code, but now we follow the fraction of gas that is accreted from or comes from each of these different sources, but to the inner region, to the middle region, and to the outer region. Okay, so if we take a galaxy and we look at the outer part of the galaxy, then we can see that for both galaxies, it's more or less the same trend. At high redshift, we have a large contribution. Most of the gas comes from what we call unbound material, so material that comes through the filaments normally, and they are cold gas and normally low metallicity gas. But then as the galaxy evolves, we have a contribution here from the circumgalactic medium in yellow, and in red, we have a contribution from what we call outflowing interstellar medium, which is the material that is being ejected, normally associated to supernova feedback, and is being accreted at some other point of the evolution of the galaxy. So this recycling of material is in red. So at some point, this is what is dominating the outer part of the galaxy. And you can see that in the inner part, well, we have also, some green part, which means the material that comes from satellite galaxies that are being accreted at different times, depending on the interaction or the history of interaction of these systems. This pink contribution is contribution of gas that is inflowing, so gas that is in the outer part of the galaxy and flows in. So in the inner part, there are not much contribution because these are the outer part of the galaxy, but in the other two, in the inner region and the middle region, we know, or we can see that there is a large contribution from material that is in the outer part of the disk, and at some point, probably because of interaction of tidal torques with other systems, it loses angular momentum and falls into the inner part. And there is also a contribution from inflow cold gas, okay? Also at high redshift. But as we move to lower redshift, in the inner part, most of the contribution comes from material that was outside of the galaxy, and for some processes, even FR formation, or as I say, tidal torques, it moves into loose angular momentum and moves in. The detailed contribution from different sources, of course, depend on the history of the galaxy. Okay? So these two galaxies have more or less the same mass. One of them is has a slightly lower mass, but they are comparable. So they more or less show the similar picture. But if we go to galaxies of different masses, we expect to have different contribution of these different sources. Okay? And this gas comes, as I said, with different property, particularly with different abundances. So let me show you some example. Now I'm going to take this part, okay, this interaction here in this galaxy, where the galaxy change the metallicity gradient in the inner part and becomes positive, okay? If it becomes positive, means that it is inverted, okay? So it received, in this case, you can see that it received, sorry, we have the change in the middle metallicity gradient, but also in the outer part. The outer part is also positive, okay? It's broken with a positive break. And in this case, so during this period, here, we try to summarize, and this is a kind of a difficult, well, it's not so difficult. So here we have a change. You don't see it here, but here it should say delta Z. So it's a change in the Z direction, okay, in the perpendicular to the disk, okay. And here you have the change in radius, okay, in the on the disk, the radial direction and the perpendicular direction to the disk. And in colors, in the first plot, you have the different sources, okay, these sources, okay. So, and here you have the fraction that each of the sources have contributed. So in this case, that there is a break, a positive break in the inner and the outer part of the disk is mainly due to this, to two sources. This circumgalactic medium, so gas that falls from the circumgalactic medium to the inner, sorry, to the middle and outer part of the disk. And because it's the circumgalactic medium, it is material that is enriched. And we can see it here. This is the median oxygen over hydrogen of this material. And it's this material, which is this one, in general, is enriched. Okay? It's a solar, even slightly super solar. In the simulation. What else we have to say? And the other contribution comes from here, which is the outflowing gas, which is mainly related with material that is either expelled by the supernova feedback or material that is being disrupted from the galaxy when the arms get distorted. And this gas is also metal rich, okay? But on the other plot here, you have the temperature, the median temperature, and you can see that the gas that falls in is lower temperature than the gas that is being expelled, which is higher temperature. So this is a way of showing that it actually fits in the picture that we have, that when we have a supernova feedback, or another piece of information is that this is a merger, an interaction going on here. So we have both things. We have maybe the arms that are the galaxy that is being distorted. There is a star formation that is being triggered, and we have supernova feedback that is being ejecting part of the material, enriched material, and is hot also. And at the same time, we have a material that is falling from the circumgalactic medium, which is cooler, but also more enriched. But not so much enriched, because we also have some, you can see some blueprints here. So it's a material that is mixed. Some of them are less enriched, and some of them is slightly more enriched. But we have also another example, which is this other period where there is a large variation, but both the inner and the outer metallicity gradients are both negative. Okay, so in this case, we have a large contribution from infalling material, from unbound gas. Okay, most of the material that falls in comes from this source, and this source is low metallicity, as you can see here, and is cold. And this material is contributing to all the region of the galaxy. So it's decreasing the metallicity in several parts. But also there is some contribution from the circumgalactic medium, which is, but it's only 20%, 26% of the material comes in. You can see also that in the central part, there is more enriched material that is slightly hotter and is always related to supernova feedback. So as you can see, this is, even in simulation, is quite complex to actually disentangle from which source which source is the one that is mainly contributing to the change or to shape the metallicity gradient of the galaxy, because they are all acting at the same time. Sometimes we can find some periods where there is clearly one that is more important than the other ones, but they are all contributing at the same time. So this is why, even in the simulations, difficult to actually disentangle some information from the metallicity gradient, but it's not impossible. It's just difficult. So we can actually follow this as a function of time. And this is an example of an interaction. For example, the first stage, the first pericenter, the apocenter, and the second pericenter. And you can actually see how the galaxy gets distorted and how the metallicity gradients change. At sometimes, I mean, it only changes the metallicity, the slope, so it gets like flatter. But at one point, there is like an increase and a break of the gradient, an increase of the metallicity in the central region, normally produced by a strong star formation. And then with the ejection of material, we lose part of the material, of the enriched material, and we flatten the metallicity gradient again. So this evolution lasts like about 1 giga-year. But we can have other examples where we start from a already broken metallicity gradient, and the supernova feedback ejects a lot of material. And sometimes it's not like it ejects material, but it heats up the gas. And if the gas is hot, it cannot form star. So we have gas here, and we have enriched gas. But if we look at the sites of the star formation, we cannot see anything. We cannot measure it. So for some time, we cannot measure the metallicity gradients in this galaxy. And then at the next snapshot, we got this inverted metallicity gradient. But just the next snapshot that we have available, the metallicity gradient is inverted again. And then it recovers the negative kind of flat gradient, and then it gets stable. And this kind of evolution lasts like about 1 to 1.2 giga-years. So it depends on how the interaction in this case takes place, because here the interaction is with this small galaxy here. But the progenitor or the main galaxy is very gas rich, so it reacts differently to the tidal torques of the exerted by the small satellite. So far, this is what we have been doing, and I have been always talking about this oxygen over hydrogen, but how do we actually measure this in the simulation, and how do we compare with observations? So in the simulations, what we do is we search for the gas that is in condition to form a star, which means that it's cold, is dense, and is in a converging flow. And then we have for each of these, what we call particles, which are actually differential of masses of gas, cold and dense gas, they have associated a mass of oxygen and a mass on hydrogen, the mass of sulfur or nitrogen, all the chemical elements that we have included. And we estimate with that the number density of the isotope or the oxygen and the mass of and the density of hydrogen, and we estimate this value. No? This is what we do in the observation, but this is not exactly comparable to what you observe, or you can say, many of you will say, this is the way we observe, and it's true. Okay. But now, in order to actually have a more comparable indicators, we actually try to estimate this. What we do, we actually develop a code that associate to each of the stellar population the seeds, and we have a spectrum, which is, you can see it here. I mean, this has been done for several years, but the new stuff is to actually simulate the emission lines. So we also combine this with a CIELO code that has a spectra line emissions model in their code, and we can reproduce this now more complete spectra for this galaxy. Actually, we reproduce an IFU here, and for each of these spaxa, we have a spectrum. And from these emission lines, we estimate the indicators now, or the different metallicity indicators that you use in observations. Of course, in order to get to this point, okay, this is, let me explain a little more better. These are the normal, or the indicators that are normally used. And this is the oxygen over hydrogen that have been used so far. Okay, this is exactly the intrinsic one that comes out from the simulation, and this is that comes out from this process of generating the spectra with emission lines, and then using these lines to estimate these abundances. So these lines here, the black line, the black points, are the results from the simulations, and we make a fit to these trends. And here the black are without dust, and the red are with dust. So the red lines in each of the plots give us the correlation, or the calibration between the abundance, the indicator, and the intrinsic abundance that we get from the simulations. So we are actually working on that, and we are actually working with the referee of the paper. And the idea will be to run this over the simulations and to be able to simulate the IFO observations, and then from there estimate the abundances, the different calibrators, and try to compare now or build up the metallicity gradients by using these different indicators. Hopefully it works. It works well enough to find something that is reasonable. So in summary, so we found in the simulations galaxies that are well defined by a single power law, but in general, they have some breaks. They have inner breaks and outer breaks. From so far, we can say that the inner breaks are sensitive to the star formation and supernova feedback. We don't have AGN feedback in our simulations. So AGN feedback is an open question, but maybe Borja will say something about it. We found that galaxy interactions and mergers, which also trigger bars at some points, and gas inflows, are responsible for the inner breaks, particularly cold flows at high redshift, and then galaxy interactions at bar and low redshift. And the survival time of these inner breaks depends on the capacity to retain the chemical elements by the host galaxy. Outer breaks are more sensitive to the accretion of material from the outer parts that comes from material that has been disrupted from the satellite galaxy or even the main galaxy by galactic outflows, and became part of the circumgalactic medium and then were accreted later on in the outer part. But also at high redshift, cold gas flows, which are lower metallicity, are important. So what we're planning to do is to extend this very detailed analysis to all the galaxies that we have, so we might be able to have a more statistical support to this claim and see if we can actually have a prediction to be able to relate the shape of the metallicity gradient and the property of the galaxy, because I think we have to look at the property of the galaxy and the metallicity gradients at the same time to have like a timer for the galaxy evolution. Thank you.
Okay. Well, thank you, Patricia, for the very interesting talk. So it's now open the time for questions. Rosa?
Thank you. Very nice result and work. I missed at the beginning, how do you think between a strong and weak supernova feedback?
When we put the only way to do this, or the way to regulate that is to decide how much energy you are actually injected into the interstellar medium. So when we modulate the strong supernova feedback, you're boosting the energy like 3 or 4 times the 10 to the 51 ergs per volt. Okay.
So don't change the number of supernova
Well, in general, I mean, you can actually, if you change the initial mass function, then you
Yeah.
get a stronger, yes, of
Feedback.
course, you get a stronger effect, of course. If we're using now Chabrier, for example, because
Mm.
it gives you a stronger effect with this, because it increases the number of massive stars. But in this case that I show, the example that I showed, they keep all the other things fixed and only change the energy of the supernova feedback to actually see the impact.
Mm.
The idea was not to actually find the best parameter, but to actually understand if the supernova feedback was able to invert the metallicity gradient. What was the impact of this supernova feedback? But yes, you can also change the initial mass function. But there is a limit, no?
Mm. Okay. Another point is, are you planning to also to do the study for gradients on metallicity, stellar metallicity?
Yes, we are also
gas?
doing that. We have started with the EAGLE simulation, and we haven't published yet, but it's almost ready, the paper. We are studying the metallicity gradient. I mean, in the EAGLE simulation, we are finding a large diversity of metallicity gradients, and it's not a clear trend. But so we are also starting to analyze here in the CIELO simulation the metallicity gradients of the stars. But yeah, the idea will be to actually put everything together. I mean, the gas phase and the stellar phase, and see when how does the star formation, the metallicity gradients of the stars and the stars of different ages change with, and also with the change in the metallicity of the gas phase. Okay?
Mm.
But yeah, we are doing that, but we are less advanced with that.
With respect to the stellar migration, are you seeing or you are?
Yeah, we are studying a little better now the stellar migration because we started, instead of starting by analyzing the metallicity gradients of the stellar population, we're starting by looking at the oxygen over hydrogen as a function of the iron over hydrogen. So this is a bimodal distribution that the Milky Way has. So when we started looking at that, we saw that there is a fraction of stars that have migrated. So we are now analyzing in the disk that we are simulating in the CIELO simulation, the migration fraction, and how does it affect the distribution of chemical elements. But depends on the system. There are galaxies that have like 40% of migration, depending where you're looking also, at what radius, and some other galaxies that have 10%. I don't have a clear answer right now. Yeah.
Thank you.
Yes, regarding the particle mass that you follow up, you said that you have some percentage of what's made of oxygen, nitrogen, etc. So I was wondering, when you show us the temperature that you see the different gas components, that temperature is based on hydrodynamical cooling processes, also taking into account atomic processes cooling the gas, or?
Yes. So this temperature has taken into account the chemical composition of the gas. So it takes into account the cooling by the different species.
Okay.
Yeah.
So if it's not accounted for AGB stars now.
No, doesn't have AGB stars right
So
now.
that's my point. And you expect that, for instance, the change in temperature, because you can have an extra cooling by nitrogen in that gas, can also affect how, because I see that there is a clear trend of how, depending on temperature, where the components are located, that maybe can change that. Because, for instance, in the outbound gas, I suspect that the composition from the outbound gas is kind of primordial, right?
It's quite low. Yes, it's lower. Yeah, it has to be low metallicity. I don't. Well, we cannot see very well here because I have everything superposed, but it's low, like 7 or maybe. There is a floor of metallicity that we can actually estimate. But yeah, when we include it, we actually have included the AGN feedback, and so AGN, no, sorry, AGB. AGB. And yes, there is a change. We also changed the cooling function, so now we cool down to lower temperature. So we have to scale all the parameters, particularly the star formation. So we are doing right now, the cosmological simulation is running to see if we can actually, because at the end, this galaxy reproduce very well the general property of galaxy. So whatever we put there, it has to, again, the simulation has to reproduce the global property of the galaxy. And we don't fine tune the chemical abundances. So the chemical abundances just are the result of what we have put as a subgrid physics. So we have to see if we get good results or bad results.
And also the rate in which they are changed is by means of the yields that are fixed, or do they change over time?
The yields?
Like how you shape the contribution from the fraction of the metals, oxygen fraction, when you change that over time because of that particle.
I mean, what we have is we have a particle which represents a differential of mass. The gas is transformed into stars, and then we have an initial mass function, and this initial mass function tells us how many stars of different masses. And then from there, we adopt a yield. And the yield, depending on the metallicity and the mass and the ages, we take the yields that correspond to that, and then we eject the material out. And then we have remnant, and this is what we follow as a stellar population.
Questions? Well, yes, in relation to that, so most of these gas is actually thermal. The temperature is about 10 to the 24, something like that. So it's a typical gas, ionized gas that you see in H2 regions, these kind of things.
But this is a gas that is coming. This is gas, most of this gas, this part is coming in from the outer part. So this is the gas that have to fall in. So at this time, which is redshift 3, redshift 4, so this is the time, this is the temperature of the bigger gas.
Yeah. So this is already like
Yeah,
the same temperature that the thermalized gas that
Yeah,
you
the
see.
thermal, yeah.
So another thing was in relation to the brakes. Is it one-to-one that you need an environment to produce a brake, or is it can you produce a brake from an isolated galaxy, or is it not?
Well, I mean, here, I don't know. For an isolated galaxy, I actually don't. Let me show you these ones are simple.
So it's strictly forbidden.
Well, more or less, because here you can see that there is kind of a break, but I don't track it very much.
Oh,
This is an isolated galaxy.
Small.
Yeah. And the only thing that it does is transform gas into a star as a function of time, and then it started with the density profile, no, the gas density profile. So I don't know if these breaks are real or they are something from the simulation, because it started here, so it already have like a break here and here, but these are the outer part and the very inner part. I don't know. It doesn't have this clear change of profiles.
So the easy way is to have an environmental cause.
Yeah, I think it have to
Either
be
tidal or
yeah, probably if this galaxy develop a bar, because that can be the thing. I'm thinking that maybe the galaxy develop a bar by internal instability, and then you can break the profile because of that.
Okay.
And that can happen.
Mm.
So the bar will be the process that.
There is some questions from the audience.
Yo te tengo.
Ángela.
Es un comentario más que una pregunta. Al final, un gradiente es un efecto diferencial. It's a very differential effect.
Yeah.
And it tells you how much evolved is one region than the other.
Yeah.
In fact, it doesn't depend very much on nucleosynthesis, almost not at all. I mean,
What sense?
so what you see there,
Yeah.
and this is very important, is that at some point, the outer region has to get flatter because abundance cannot be infinitely low.
No, yeah, that's true.
Okay.
Yeah.
And this happens also in observations. That produces breaks, let's say. I mean, in that galaxy, you are not getting to very low metallicities. You are getting to a metallicity half solar or so, 8.4.
Here, yeah, but remember that this is a galaxy that I built up, no?
Yeah,
So I
yeah.
put in an initial profile. Yeah. Okay.
But if you do things in reality, you are going to produce a break or a flattening anyway in the outer parts.
Yeah, because
So-
there is like a floor.
So-
yeah.
What I'm saying is that you have to be very careful because a differential effect gradient is going to be weighted for the abundances in the central part, which we don't know at all, and we extrapolate,
Mhm.
and the ones at the very out. All the rest in the middle is working fine.
Mhm.
But when you change something here or something here, you change the gradient.
Mhm.
So you need to be very sure that the abundances at the two ends are well determined in order to have a good gradient. Otherwise, you mixed it all.
Mm.
And this is a problem from the simulation. But because depending on the galaxy you are simulating, you are going to get galaxies which are very evolved in the center.
Yeah.
In the gas in the outer part is not doing anything,
Yeah.
and you get with this right steep gradient, or just the contrary.
Yeah.
And the other thing I want to comment is that if one thinks in these terms, which is the reason why the first view graph you showed was this perfect gradient in the inside-out formation scenario,
Yeah.
is that it's very difficult with that in mind to get a negative gradient. Because it means that the outer part is much more evolved than the inner
And I
part.
got a positive gradient.
Even positive.
A positive.
Yes,
A
yes, of
positive
course, it's
gradient.
impossible.
Then
Yeah,
when
yeah,
you
yeah.
find the positive
Yeah.
gradient, something has
It
happened.
has happened, exactly.
That's it.
This is why I think it's very, they are very interesting.
This is the most
But-
important part of it.
I need a
Tell me more about those galaxies.
Yeah.
People about
Yeah,
that.
yeah.
Because if you find that,
Yeah.
and this is well done and well documented, and it's the abundances are rightly derived, if you get a positive gradient, then something has
Has
happened.
happened, yes.
An important merger
Anomalous, I mean, anomalous.
of things.
Yeah.
Not anomalous,
Large
just things.
inflow,
Environmental
gas,
things.
yeah.
Some
Strong
some merger that you don't see any longer, but has happened in the past.
The thing is, how long does it take to go back to, if it does, go back to
But-
that's, yeah.
But it
I
is
agree.
very important
Yeah.
to get that, because otherwise we are always saying, well, it's not conclusive, this can be this, it can be.
Yeah,
It
that's true.
doesn't
I should
help.
have pointed out better that if there is a positive metallicity gradient, it means that something
Something
happened.
is happening.
I agree totally.
Because
Yeah.
otherwise, your main assumption that you did at the beginning breaks down.
Yeah, that's fine.
And then we have to
No,
start
I
over.
think that is the. I started this, got involved in the metallicity gradient and never got out because of the inverted, the positive metallicity
Then
gradient.
in the inverted
Because-
gradient, I mean, if it is well,
Yeah, if it is,
and it's a good result,
yeah,
then something has
yeah,
happened.
yeah.
And now you have all many possibilities to get it right, but something has happened.
Yeah.
And if you cannot find any way of reproducing it, then the main assumption
Yeah.
made at the beginning breaks down.
Isabel?
Yes, can you hear me?
Yeah.
Okay, thank you very much, Patricia. Very nice talk. I have two questions, but very short ones. The first one refers to the plots you've shown where you compare the observations with the simulations in terms of, so to the right, there were the plots with the distance to the center. And I guess that I've seen that the points the observer galaxies have data for much closer to the much farther to the center than the simulations. So is that my impression, or is that true, and why is it so?
So I understand the first one. The second one.
That's the first question. That's just one question.
Okay. Well, in the simulations, we are of course limited by the numerical resolution and the gravitational softening. So in general, the simulations that I have shown cannot go to smaller. I mean, the closer to the center is about 200 parsecs or 300 parsecs. I'm not sure about the observations. I think the observations.
But I'm referring to the outskirts. It seemed to me that the points you're showing for the observations reach much farther out in the galaxy than the simulations.
Maybe, yes, because for example, here we don't. This is the gravitational softening.
Mhm.
I mean, I don't know if you can see it.
Yes, I can see it.
Yeah. Okay. So here.
Well, I don't see your cursor, but I see the plots.
Can you see my arrow?
Yeah, that's okay now.
So
Yes.
this line here is the gravitational softening. So we cannot go inside to this region. So this is about, in this case, in this particular simulation is 400 parsecs. So this is why we don't see anything here, because there are very few particles, and also in general they are also hot. And
But,
so
but I'm referring to plots that you've shown before these ones. So so
these are observations, but I didn't show a profile, only this one.
no, but you were showing plots when you where you compared, so it must be further. Where you were comparing observations with simulations, yeah, those kind of plots, exactly.
But these
Exactly.
are mass, no? These are mass and gradients.
Yes, but in the plots to the right, where you are plotting points in terms of the distance to the center.
This is this one.
Yeah.
This is the radio. No.
So the observations are
This one, the opens.
and the observations provide you with points that reach until 14 kiloparsecs, but the simulations don't reach those regions.
Yeah, this is because we are looking at, in the simulation, we have galaxy with the smaller masses. So these are, here the red points are the simulations, and you can see we go 10 to the 5. And these galaxies are more extended and more massive.
Okay, because they're just bigger. Okay,
Yeah.
okay.
So
Thank
we're
you.
limited with the range of masses that we are covering in the simulation.
Okay, so it's a result of the difference in the selection in mass. Okay, good. So my second question was, do you have plans to incorporate the AGN feedback in your simulations?
Yeah, we are working on that, but it's not so simple, but we're working. Yes.
I see, because I will be very much interested in when you will have those results, since I'm working on AGN, so that'll be great to have these results on hand. Okay.
It's not so easy.
Yeah. Okay, so thank you very much.
Yeah, thank you.
Any more questions? Sorry?
Yeah.
So it's regarding the last part where you simulate the emission lines from.
Yes.
What all properties do you keep in mind? Go from particles to emission lines. Like
Yes. Yeah, to go to to get emission lines, we need to simulate also the surrounding region, no? The ionized cloud, and that's the problem. So what we are doing, our model, what it does, it takes the closest particle, gas particle, to the stellar population, the young stellar population. We take the closest gas particle, and we take the properties of that gas as representative of the age duration. So we take the metallicity, the temperature, the density, the electron density, and with that we build up, or we estimate, the ionizing parameter, which is what we actually need. And with that, then it's all right, because you have the ionizing parameter, you have the size of the region and the property, the metallicity, and with that you can get into the code, in this case SIGAL, and retrieve the lines that correspond to that, and the star formation line, no, the young stars. We also have the emission, the photon emitted by the population. And with that we have the emission lines. Yeah. but it sounds like it's simple, but it's not complicated.
Patricia Sanchez Velázquez was online, but she left because some reasons, but
So she has two questions. Do you have plans to analyze the gradients of stellar abundance? Maybe, maybe comparing both of them, you can try to distinguish processes in the observation.
Yes, yeah, she asked that, and because I wanted her to be part of the.
And
We talked about it, yeah.
and the second one is the gradients in simulations. You usually express index over kiloparsecs, and in observation index over radius, I think. That could change the relation between gradients with mass.
Yeah, we actually do both things. We actually estimate it as a function of in kiloparsecs and in dex per half mass radius. And in general, yeah, I mean, we have used here. We have to choose at some point because at low redshift, or redshift 0, there are a lot of observations that give us in half mass radius, like normalized by the half mass radius, and that's fine. But as we move to higher redshift, there are no way of getting the same thing, so at least not yet. So we change and we use like kiloparsecs. But yeah, that's true.
I think we have to stop as
Yeah.
because we have a telecom later,
True.
but just looking forward for introducing also nitrogen in the simulation.
Yeah, yeah. Great,
you.
thank you.
Yes.